right, good afternoon, everyone. Good afternoon. 12:50, I am recording this lecture. I hope that you found Wednesday's lecture on our Canvas website. Remember, I try to record every lecture just so you don't get too far behind if something happens and you can't make it to class. All right, so the first thing we're going to do today is we're going to have one top hat question. So if you want to get out your top hat devices, that would be great. This is just a trial run. I will not take this for points, so don't worry if you haven't registered yet. But next week, starting on Monday, I will start taking top hat questions for participation points. Okay, so let's get going here. Open up our top hat accounts, get your devices ready. Let me just make sure I'm in the right section here. All right. For those that just came in, we are going to take one top hat question this morning. Afternoon. I'm sorry, afternoon. Thank you, Megna. That's why she sits right next to me. All right, so here we go. Let's get this on the screen. Here is our first question for today. All right. Our section is 446426, and if you've never done top hat before, what you're going to need to do is text 3405 and your response, either A, B, C, or D, to 315-636-0905. Okay, so the question for the day is, what are the three major themes of physiology? A, Homo sapiens, contraband, and using the force. B, homeobox, controllers, and fluxes and farce. Or C, homeostasis, control systems, and forces and flows. So this is straight from Wednesday's lecture, or D, none of the above. So go ahead and answer the question using top hat, your top hat device. Shouldn't be too hard today. And this is basically what we'll do in the beginning of every class period. So just to get used to this. All right, what do we have? We have about 75 students or so that have already answered. Great, great job. When we get to 80, I'll give you about 10 more seconds. Okay, anybody having any trouble answering today? Device, okay, no worries. We can talk after class too, and I can walk you through it if it's not working for you. So remember, with these top hat questions, you're going to have at least 12 opportunities, and you get to drop 2, okay? So on the back end, like weekly, I will take one of the questions each week, and I'll put them in the grade book. I'll put your scores in the grade book. All right, so we have 82 students. I'm going to give you 10 more seconds. All right, and again, if you're having any trouble, don't worry. We can figure it out after class, okay? So go ahead and close this, and the correct response is C. Right? C. All right. Everybody got that right. I'm glad. So I can assume that you were listening on Wednesday, which is wonderful. All right. So with that, actually, that leads us to the last part of the first lecture that I gave on Wednesday. I want to just finish up by talking about control systems and forces and flows. We'll go through Ohm's law in just a little bit, okay? All right, right after that, we're going to take a little break, and as promised, we're going to get into our groups for the group video project, okay? So I'll give you some time to introduce yourselves again to your neighbors. I know you did that on Wednesday, but we'll get into our groups, and you can start picking your topic. All right, so let's go ahead and get to where we left off. Through homeostasis, if you remember, and we had a small active learning exercise to kind of think about some of the biological processes within the body that actually have mechanisms in place that maintain homeostasis. All right, so let's get to that part. Sorry, I'm scrolling all the way through here. It's all the material that we covered on Wednesday. It is a lot. And this is where we left off, if you remember. Whoa, stop. Ooh.
Sorry, was that me?
Oh, no, that wasn't you at all. I think I just scrolled through too fast. So here's where we left off. Now we're going to start with control systems. Okay, again, this is one of the 3 major themes in physiology. Again, these themes in physiology are what distinguish this discipline from other disciplines like biology, biochemistry, zoology, okay? So this is what makes physiology unique in that a lot of what we're going to be talking about adheres to these 3 major themes. So the second one is control systems here. Remember, control systems perform the compensating regulatory responses to maintain homeostasis or a relatively stable internal environment condition. All right. So here's where I want to start. I'm going to start by talking about negative feedback mechanisms. Okay, so just to open it up, you'll notice that there's going to be a lot of illustrations of negative feedback mechanisms, especially when we get to hormones. Okay, here's one that I just like to roll out, a classic example. This pertains to more of the heating and cooling system in your house. Okay, so what we have here is 3 components. These are the necessary components of a homeostatic system. You have a receptor, a control center, and an effector. And this is how it works. Like any heating and cooling system, you do have some kind of sensing mechanism that's actually going to sense the temperature in the room. Okay? So this senses the temperature, and you have a thermostat, which you control. You actually you have a set point that you actually dial in, right? And if there's a discrepancy between the room temperature that's sensed by this thermometer and the set point, if they're not equal and there's a huge discrepancy, what's going to happen is it's going to trigger an effector. And in this case, if the room is too warm and that's not where the set point is, then it's going to turn on this fan. Okay? So that's the effector. And once the fan is turned on, it's going to cool down that room, getting it closer and closer to the set point value. And once the room actually reaches that set point, it's going to turn off the fan. Again, this is what's called a negative feedback mechanism. Okay? Pretty good? So that's one of the necessary components. The next one I want to roll out is basically a positive feedback mechanism. Okay? So the classic example of a positive feedback mechanism is basically where the output acts as a further stimulus. Okay? And what happens is, okay, so let's take the classic example of oxytocin. Okay? Oxytocin is a really important hormone during labor when a woman is actually having a baby, right, during the birthing process. So what usually happens is oxytocin is released. It actually causes uterine contractions. And then when uterine contractions occur, that signals the posterior pituitary to release more oxytocin, which causes more contractions, which then signals the posterior pituitary to actually release more oxytocin. You can see that this response just gets more and more amplified until a major event like birth occurs. Okay? So this is a positive feedback regulation. A lot of pathophysiological states actually this is what happens. Positive feedback mechanism occurs until something like death occurs, right? Now, not all positive feedback mechanisms are a bad thing or abnormal, okay, or a major event. We're going to learn when we talk about calcium regulation, sometimes there are mechanisms where calcium floods into the intracellular space, okay? We'll talk about GQ-coupled receptors, right? A lot of calcium floods into the intracellular space, and that triggers certain receptors to release more calcium, right? More calcium is released. That triggers more calcium release. That's not abnormal. That's actually part of a normal process within the cells. It's just this positive feedback mechanisms help to amplify the response, okay? So not all positive feedback mechanisms are abnormal or a pathophysiological state, okay? So any questions about that so far? All right, just wanted to roll that out. Let's just bring it home with a formal definition here. These are negative and positive feedback mechanisms. The negative feedback mechanism, this is where the output reduces the stimulus. So again, as that fan turns off and cools off the room and that temperature gets very close to the set point, it turns off the fan. So it's self-regulating. It helps to maintain homeostasis. And a good classic example is body temperature. And these mechanisms really vary in complexity, and we'll get to that as we go through the semester as well. The example that I use for a positive feedback mechanism is oxytocin, and this actually disturbs homeostasis. This is where the output actually acts as a further stimulus. Good? All right. Let's go on to forces and flows. This is actually one of my favorite ones. This is the role of transport in physiological systems, and we'll be talking about this quite a bit with cells. Now, this chart is actually in your syllabus. If you haven't read through your syllabus and found this chart, I highly recommend that you do. It really kind of helps tell you where we're going in the class here. We are, next week, when we talk about diffusion of charged particles, we're going to be talking about Ohm's law in terms of electrical terms. All right? So let me go ahead and actually just roll out Ohm's law here really quick. Let me find a sheet of paper I can use with the document camera. And like I said, Ohm's law, did I talk about this before? Driving force? Oh, okay, good. I don't have to spend too much time. Okay, so then we're not going to do that. Thank you. With 2 sections, it's hard to remember what I've talked about and what I haven't. All right, so what we're going to do is I just want to kind of tell you where we're going. Today, we're going to focus on Ohm's law in terms of the chemical perspective. We're going to be talking about net flux in terms of moles per second. In this case, the driving force is that concentration gradient. And the resistance factors are viscosity, particle size, permeability, and diffusion distance. Okay? This is all kind of woven into Fick's law, which we're going to be talking about today. Fick's law of diffusion. Next week, when we talk about diffusion of charged particles, this is where we're going to be talking about the resting membrane potential. So you have to know something about these electrical terms. I'll roll out what is current in coulombs per second. This is a unit of charge that's per second, like a river of charge, actually. Okay, so this is still flow. The driving force is a voltage gradient, and resistance is resistivity or conductivity. They're the inverse of each other. And the diameter of the conductor, like the diameter of an axon. So you can see where we're going to apply this when we get to neurons. Okay? All right. Then when we get into cardiovascular and the respiratory system, when we specifically blood flow, hydraulic terms, we're going to be talking about blood flow in terms of liters or mils per minute. Like a garden hose physiology, that's what I talked about on Wednesday. The driving force is going to be the pressure gradient, okay? And the resistance factors are the viscosity of the blood, how thick it is, the vessel radius, and the vessel length. So in this course, you will participate in many integrative exercises, and it's with these interrelationships in mind that the material for the course has been organized. So that concludes that first lecture. I just want to make sure that you had that material on control systems and forces and flows. What I'd like to do now is just take a break. And basically, I want you to get into your groups. Each table should probably just divide into two. And you can start thinking about your project. Let me go to the document camera now. I'll show you what I'm looking for. I do want you to turn this in on Monday so I can actually start to get everybody in their groups and identify it on the Canvas website. What you'll need to do, so this says Monday, this should actually be the 27th, so I got the date wrong there, sorry. But Monday, please put a creative name for your group. Your group members, I don't want more than 5 per group. And then go ahead and let me know, what kind of project did your group decide to do? You can do an educational video tutorial. So that's something, if you've mastered a particular concept in class and you really want to teach other students, maybe an easy way to study or a creative way to think about it, then this video is for you. All the videos should only be between 3 and 5 minutes. Physiology in the news, physiology advancement, a pathophysiological state, maybe comparative physiology, or an animation, or be creative, do something completely different. Okay, and then rank your topic 1 through 5, 1 being your top choice. And I want to just make sure that all the topics have been spread out and that they're all represented. All right, so I'll give you about maybe 5-10 minutes. Talk to your group members. You know, if you have any questions, just come on up. All right? All right, good luck. Oh, of course. Yeah, there's plenty of these copies. There you go. Yes. Oh, absolutely. There's plenty of extras. There you go. Yep. Did you need one of these? Yeah. No problem.
Does everyone turn one in, or just
no, just the group? Yeah, just one for each group. Yep.
Here's how it works. Here's what, yeah.
Do we all fill it out, or do we just submit one?
Yeah, just one.
Okay.
Yes, but I gave everyone one just so that you have some.
Great.
All right, I've had a couple of really good questions. Each group just needs to turn in one sheet. Okay, not everyone needs to turn it in. Just one sheet for each group.
Do we just like check which ones we might want to do, or like?
I would just choose one of those,
Okay.
and then rank your top.
Rank top. Oh, for this part. Yeah.
Yep.
Okay.
That's okay. I deal with that all the time, so I will make sure. If I come across one of your assignments that isn't decided correctly, I might email you and say, hey, is this you?
Yeah.
Okay.
If you need a reminder, just email me too, so you're not.
Okay, that'd be great. Yeah, that'd be great.
Perfect.
Hi. Do you need a sheet?
No, I'm good. So
Okay.
I actually just joined yesterday.
Oh,
so
sure.
I wasn't here for the lab.
Not a problem. Okay, so for the lecture?
I wasn't here for the lecture or the lab.
Oh, okay.
On Wednesday.
Okay, no problem. You may or may not know this already, but I record every single lecture.
I did see that, which
Okay.
is great
Yes.
because I'm also in the National Guard. So I'm
Perfect.
do you want me to email you my drill
Sure,
schedule?
you can do that just because then I'll have a record of when you're gone, and if you want to make up top hat questions,
Okay.
right, then we can do it in my office, and then I'll know exactly which days you're gone. Some students come into my office and say, I missed top hat number 5, and and they're not sure which date, so that'd be great.
Okay.
Yeah.
I can either prefer me to print it off, or I can email you. I can have,
You can
like, a
email
memo.
me. I'll just keep that email and I'll have it as a record.
Okay. So
Yeah.
I know I will miss 2 labs.
Okay. All right. Magna is actually your lab TA.
Oh,
Yeah. So you can talk to her after class if you'd like.
Sounds good.
And she can get you caught up on the day. They basically just went through the syllabus on Wednesday, but on the days that you'll have to miss the lab, she can get you caught up.
Uh-huh.
Yeah. So it's
Okay.
Jess and Magna. They're both your TAs for that.
Thank you.
Yeah. Hi.
Completely blanked, and I forgot to print out the problem so that I could.
No, I actually printed out plenty.
Thank you.
Yeah, you're welcome.
Are we turning this in to you?
Yes.
If we're
Are
done?
you all ready? We are all done.
Dunsies.
Sweet. Okay. All right. If you can finish up here in the next couple minutes, I already have a group that's actually turned theirs in. What I'd like you to do is once you've filled it out, just throw it in the middle of the table, and we'll go around and pick it up right after class. Okay? I can do that over the weekend.
I realized a couple people don't have them.
Oh, sure, absolutely. So you need the group video project?
Yeah, the group
one?
video,
Yeah.
like 4 of them.
Okay, sure. Actually, we got plenty. So there you go. Yeah. All right, everyone. I better get through some lecture material today. So I'd like to actually get through diffusion of uncharged particles from the continuum perspective and from the random walk. We'll see how it goes today. We won't be able to get to osmosis today, I'm pretty sure. So your problem set number 1 won't be due until Wednesday, and I'll change that on the Canvas site, okay? Because I want to make sure we get through osmosis. The last 2 questions actually pertain to that. So, all right, so let's switch over, everyone. Here's where we're going in the next few days. The first 2 topics we're going to cover today are diffusion of uncharged solutes from the continuum perspective and from the random walk perspective. And then we'll get to osmosis on Monday. All right, so I do have a list of learning objectives. I'm not going to read through them, but if you want to kind of go through them on your own when you get home, that would be wonderful. I'm going to start right away with these illustrations, and we're going to talk about what is diffusion and what is diffusional equilibrium. And the reason, again, why we start with diffusion, a lot of people think, oh, that's pretty random. And that's not a pun for random walk perspective. But the reason why we do that, the reason why we start with diffusion is because every organ in your body relies, this is one of the fundamental concepts in these physiological processes. Again, especially with the kidney, it is all diffusion and osmosis. So you really need to understand this to really understand the kidney, especially. So let's just pretend that these are 2 tanks of pure water, okay? 2 tanks of pure water. Let's start with the top illustration here. And if I dump a whole lot of an uncharged particle, like glucose, into the left-hand side, over time, what's going to happen is due to random thermal motion, these molecules are going to redistribute themselves until they're equally spaced apart. And that's what we call diffusional equilibrium. Pretty easy, all right? But these are 2 major concepts, and I do want to roll out a formal definition of both. Terminology is actually really big on the first exam. So the first one is diffusion is the movement of molecules from one location to another as a result of random thermal motion. That's diffusion, formal definition. And then diffusional equilibrium. Random thermal motion will redistribute the solute from regions of higher concentration to regions of lower concentration until the solute reaches a uniform concentration throughout the solution. That's what's called diffusional equilibrium. Okay, so I want to make sure that I write it all down for you. All right, so try to commit this graph actually to memory because I have this cool computer simulation a little bit later on after we talk about diffusion of uncharged particles and the diffusion of charged particles. So you'll see this again. What it shows you is these are, let's just take the top left-hand side here. This is two cubes that are separated by a semi-permeable membrane. And what you see is there's two compartments. In compartment 1, there's a lot of glucose molecules. In compartment 2, there is none. Okay? And over time, you actually see that they will redistribute themselves until they reach diffusional equilibrium. Okay? What you see here is this graph represents these 3 different time points. Time A is right here at the beginning of the graph where there's nothing in compartment 2. This line right here, you can actually see on the x-axis, is time B. And some of the glucose molecules have migrated over to the second compartment until time C actually shows you this is where diffusional equilibrium occurs. Okay, so you can actually see that the concentration change can be illustrated as an exponential function of time. Okay, so again, you'll see this again, and I want to just make sure that you kind of commit this to memory because I'm going to compare diffusion of uncharged particles to diffusion of charged particles later on. All right, so taking a look at this particular beaker, you can actually see here that we have 2 compartments, again, in a semi-permeable membrane. On the left-hand side is high glucose concentration, and on the right-hand side, low glucose concentration. Now, let me just explain what the continuum perspective is. This actually was put forth by Adolf Fick in the middle of the 1800s, around 1850. And the reason why he came up with his Fick's law of diffusion is because he had read a paper about 30 years earlier from Joseph Fourier. Joseph Fourier actually came up with his ideas on heat transfer 30 years earlier. Okay, so think about this. A lot of people didn't know how heat was transferred at the time. So an illustration is if you think about 2 marbles, like blocks of marble, and one it has, you put in the sun, the other one is in the shade, so there's a huge temperature difference. The rate of transfer of that heat is going to be due to the temperature difference, the surface area where they touch each other, right? That's going to also contribute to the rate of heat transfer. So there was a lot of variables that Fourier put forth that Fick actually realized I can apply this to diffusion, right? So he actually thought about it this way. These glucose molecules he imagined as like billiard balls, solid mass of molecules that move in a straight line until they collide with each other or happen to collide with a pore and move across that semi-permeable membrane. Again, this is what's thought as the continuum perspective. This is how Adolf Fick actually imagined it. Okay? So again, billiard balls moving in a straight line until they collide with each other, and then eventually they can move into a pore and across the membrane. Now, I get this question a lot from students. Are these molecules moving in both directions? And the answer is yes. Okay? You have a unidirectional flux in both directions, but the net flux is always going to go from high concentration to low concentration. So I'll say that again. The net flux will always proceed from high concentration to low concentration. Okay? So again, this is what's called the continuum perspective. All right, any questions so far? Pretty intuitive at this point. All right, so let's roll out Fick's law of diffusion. And you may say to me, Dr. Palmer, so easy. at first. Now you're killing us, right? No, this is easy, all right? I'm going to break it down for you. It's not bad at all. Okay, so what this equation is saying is the net flux in moles per second is equal to minus the area of the semi-permeable membrane. So if we actually turn this on its side about 45 degrees, it would be centimeters by centimeters, right? Okay, so that's the area, the surface area. Diffusion coefficient, that's D. In a minute, we're going to break that down into different variables. At the bottom, you can actually see how to think about the diffusion coefficient. It's equal to Boltzmann's constant, that's K here, times temperature. And you can think of KT as the thermal agitation. Okay? Over pi, 6 pi, R is the radius of the molecule, and V is the viscosity of the solvent. So the higher the viscosity, I would say the more thicker that solvent is, like syrup. The lower the viscosity, the more it's water-like. Okay? So that's viscosity. So let's go through this fairly slowly. If we're talking about the unidirectional flux, right? This is the flux from the outside compartment to the inside compartment. We can say that that unidirectional flux from here, the outside compartment, to the inside compartment, is proportional to the concentration outside, right? That's the compartment on the left-hand side here. The unidirectional flux from inside to outside is proportional to the concentration inside. So we can actually write it here. I'm right at this third line here. The net flux is proportional to the concentration difference, or the concentration gradient. So we can add now a proportionality constant, Kp, add that to the equation, and now we can set it equal to each other. But we have to define Kp, right? This is kind of undefined. So now we can say net flux is equal to the proportionality constant times the concentration difference, outside minus inside. And let's substitute that proportionality constant with area, the diffusion coefficient, and the membrane thickness. Okay, so delta X is actually the membrane thickness. Now, on your exam, you're not going to have to run any numbers, all right? The questions are going to be more like, if the radius of a molecule increases, right, or you're comparing a molecule that has a larger radius, what's going to happen to the net flux if everything else stays the same? Okay, so what will happen? If the radius increases, we're comparing two radii, two molecules, what's going to happen to net flux? Is it going to increase or is it going to decrease? It's a hard one. You can talk to your neighbors. How's that? What do you think? Anybody want to take a guess? What do you say? If you increase the radius, what's going to happen to the net flux? It's going to decrease. That's absolutely right. So if you increase the radius, you're actually going to decrease net flux. Here's an easy way to think about it. I think this is a kind of something that If you look at the equations, it's easy to answer these questions. Anything in the numerator, right? Temperature, concentration gradient, area, has a direct relationship with net flux. So if you increase the concentration gradient, you're going to increase the net flux. Does that make sense? Okay. Anything in the denominator has an inverse relationship with net flux. So if you decrease the membrane thickness, that's going to increase net flux. Or if you decrease the radius, that's going to increase net flux. So it's all about the relationships, okay? Now let me just ask you a question. All right, why is it that when you decrease the membrane thickness, or I'm going to say increase the membrane thickness, if you increase the membrane thickness, why is it that the net flux goes down? So let's take a look at here. If you increase this membrane thickness here, why is it that net flux goes down? Just thinking through this a little bit. What's that?
I mean, like, there's like kind of two ways you can explain it. So like, if you're thinking of it like mathematically,
yeah.
So like when you have a bigger number at the bottom of or like the
yeah.
denominator, it's gonna give you a smaller number.
That's right. So you can look at the equation. You can absolutely do that, and then kind of mentally think about that.
And then you can just look at the picture.
Yes.
So if the membrane is bigger,
yep.
I'll just think theoretically like, okay, it might take like a longer time for like the
exactly.
particles to go through.
That's right. So it's going to take longer to actually go through the pore to the other side, but also it's going to increase the chances of backscatter. Like this molecule is going to enter into the pore, bounce around, and pop back out the same side. That's called backscatter. So that's another kind of physical way to think about this as well. Yes, thank you for that. Okay, so one other thing that I want to mention, that this is going to be important when we actually get to the diffusion of charged particles. This idea of the continuum perspective, you can look at this concentration gradient as a chemical gradient, right? Sometimes it's called a chemical force. All right, I'm actually going to expand on that a little bit and call it a statistical force. It's not a real force, but it really is all about probabilities. Think about that, probabilities. The probability that one of these molecules on the outside compartment is going to collide with another molecule and move across the pore region is greater going from outside to inside than it is going in the opposite direction from inside to outside. There's going to be a lower probability of these molecules colliding with each other from the inside compartment and going across the membrane. Okay? So I'm actually going to expand on this and call it a statistical force. It's all about probabilities. So concentration gradient, chemical force, and statistical force. Now, why is there a negative sign here? What's that negative sign all about? It's really, this is an actual absolute value. What is that negative sign? The net flux is always going to proceed from high concentration to low concentration. So the graph actually looks something like this with a negative slope, right? So that negative sign is more about directionality, right? It's really telling you that the net flux is always going to proceed from high concentration to low concentration. Okay? Pretty good. All right, so what I'm going to do right now, get through a lot in 5 minutes. And we'll finish up with the random walk and osmosis on Monday. So hold on. Don't move. All right, so let's start with it as soon as this comes up. All right, this is still diffusion of uncharged particles from the random walk perspective. All right? So this is all about Albert Einstein. And what I'm going to say is a lot of people think diffusion is boring, and it's not boring. This is actually some drama that happened in like 1905, right? Around that time, Albert Einstein actually saw diffusion completely differently, and he turned it on its head, right? So what happened was Albert Einstein actually saw diffusion like hopping fleas. Has anybody looked under the microscope and actually seen little particles that look like they're hopping up and down, right? That's something called Brownian motion, Brownian motion. And Einstein recognized Brownian motion. And he said, you know what? I can come up with an equation to describe diffusion in a completely different way. Not from the continuum perspective, like Adolf Fick, but he saw it as these particles randomly walking around, right? This is a kind of graph from Jean, again, French, Jean Perrin. I know I butchered that, I'm so sorry. And it shows 3 different molecules with 30-second increments, and you can see the very random way that they move about this grid, okay? Actually, Jean Perrin won the Nobel Prize in 1927 because he verified Avogadro's number with his observations, which was really cool. All right, but this is Einstein's idea. He came up with this equation, x squared equals 2dt. Okay? The brilliance of this, the elegance of this, is that he can show the relationships between distance and time. Distance and time. Now, how did he do this? How did he come up with this equation when it's a fairly very random walk? I mean, who's going to make sense of that? Well, Einstein saw that, and this is a very two-dimensional way of thinking about things. When you get to 3 dimensions, that equation really expands. Okay, but in a two-dimensional way of thinking about it, for our purposes, if you line 1,000 molecules on this 0 position, and molecules can only move to the left 1 unit or to the right 1 unit, right? And then once they hop to the left, maybe, they can only go further left or back to the original position, okay? Over time, what you see is a very nice Gaussian curve, right? So the probability that a molecule went left the entire time is pretty small, right? So Einstein recognized this. He actually kind of characterized the area underneath this Gaussian curve, and he came up with this equation. Brilliant. All right, so you will be running some numbers with this one. What I'm going to say on Monday is this actually illustrates, once you start running those numbers, that diffusion is limited over macroscopic distances. And I'm going to leave it there. I'll explain that on Monday. All right, have a great weekend, everyone. If you have any questions about Top Hat or the group video project, just come on up and we'll discuss it. Hello. Yes.
From the formula. So if you said if you increase the radiation, these parts will increase.
Yeah.
And the flux of the net will increase.
That's right. So the radius, if you increase the radius, it's actually, when you're comparing 2 like dye molecules, this one is going to have, if everything else is the same, this one's going to have a much higher net flux because of the smaller radius.
But there is a negative.
Right. The negative sign really only is giving you, because this is more of an absolute value.
Oh, okay.
Yep. And the negative sign is just telling you directionality. That the net flux always goes from high concentration to low, and you have a negative slope as a result.
Oh.
Yep. Yeah, you're welcome.
For this one, when people calculate stuff, I know we're not going to run running
No.
numbers, thank God. But,
With this one we are, but
yeah,
with that one, no.
Yeah, I'm okay with
Yeah,
that.
okay.
So when, let's say you're running a number or something, you get an answer here. Do you multiply by negative?
You would.
Can I just
You
do this
would.
one
You would
here?
make sure that
perfect.
once you calculated all this, you would switch the sign
Thank you.
over.
Okay, yeah, that's what was confusing me. When I was like, when this goes up, I was thinking like, I got to like, it would decrease this, but then I'm like, multiply by negative.
Right.
And these are extra.
That's
And
right.
then my question
Yeah,
for
you can leave those
retaking the exam.
Thank you.
How bad do you have to do to take the exam?
You can retake it no matter what.
That's really cute.
Even if you got a 96 and you want to get a 98, you can retake it. I just take the top score.
Yeah.
Okay, and then what else am I gonna ask you? So you said you do that
Yeah.
Yeah.
during your
So I
final?
see the name on them.
So the final exam, you have 2 hours. The first hour will be devoted to GI and endocrinology, and then we'll be done. And then the second hour, you get to retake the exam.
Can people do like 2 hours before the final?
I'm waiting.
It really doesn't take 2 hours because the GI and endocrinology is just like one of the midterms.
I think she would be, once you let the DRC know, they email her and she submits a paper copy of the exam to them.
Okay.
Because I don't think they do online
That's right.
exams.
So my brother's wedding is on.
But we had a
Yes.
student,
Yes.
So if there's any chance, like if we could take it on that
semester,
Friday beforehand
and
or
she emailed the
Yeah,
DRC to
yeah.
contact the doctor
So
and then
we will
she would send
probably
in
have a review session
Okay,
on that
so
Friday, and
that's all I
maybe
know.
even one outside
Thank you.
class.
What's your name? Sabrina.
Okay. You might have to miss that, but you know what?
Okay,
I actually
yeah.
did you email previous review sessions, and then you can
No,
just
it's
practice
okay.
that.
It's totally fine. That's most likely how it
Yes,
works.
you're welcome. Of course. Yeah. We
I
can
did
talk
email
about it.
for my
Okay. Sounds good. Yeah. Perfect.
But the DRC
Okay,
will-
so the first problem set due
Once
Monday.
they contact her,
Wednesday.
send in
Wednesday.
Because I'm
Okay,
running
thank you.
a
No worries.
tad behind.
Okay.
So I actually want to get through osmosis.
extras. Thank you.
And then you can go home and finish up the problem set and then turn it in. I like to actually turn it in right away because then Meghna can grade it while we're in class and she can hand it back to you right away. And then you can have it as a study aid. So that's why I'm going to change it on Canvas and postpone it till to Wednesday.
Question.
Yes.
So if somebody